let's start with something that we all know that actually works. Okay, and then we'll go to something that doesn't really work, which is robotics. So we know that AI models are really good at being a generator, right? You can give it a text prompt, like, okay, generate a video of people on the beach and show me a shark uh, coming out and surprising people. And this is what OpenAI Sora can do for you. This is actually outdated, so now it can probably do much better than this. The other thing that we know that AI models are really good at is being good recognizers. So what I mean by this is you can feed in images of this sort, and we have AI models right now that can take this in and recognize that, oh, there's like a person over here. This is sky. If you care about things inside your home, okay, here's the fridge, here's the countertop, and so on. So this type of understanding is already there. We already have these types of models. Okay. So for roboticists, right, a big question from the AI side is how do we build a similar capability for robots that can interact with the world, do things to the level that we are seeing in the more digital age, right? And one approach is to sort of follow the approach in what language and computer vision has done, which is learn everything from data, or a tabula rasa approach. The idea here, you take as much data as possible, fit it in as large models as possible, and then you keep improving this model. Deploy the model, get more data, keep on training on on these type of models. Okay. So when I started my PhD a long time ago in 2014, we worked on this project where we had a robot just trying to grab objects on the table. It would then learn models of how to grab objects, and then based on the success or failure, keep retraining its models. And this worked fairly well. We then saw folks scaling this up. So there was the Google Arm Farm project, which then had multiple robots running all in parallel, collecting more data and improving the performance. Okay, so this is like 2015, 2016. We are in 2025, right? So what's happened since then? So what's happened since then is there has been this huge effort in the academic community, also folks at Google, a bunch of other startups, where the emphasis has been on trying to scale this idea up. Just get as much data on as many tasks as possible and just see where it can actually take you. Okay? But what I'm going to do in this talk is sort of go against the grain of all of this and sort of question this need of just pure data scaling. Okay, so is data scaling all you need in robotics? Maybe, but maybe in the future it's going to work. But I'm going to argue for today that no, this is not how we should build robot models, and instead take a more, I would say, intellectual approach. Okay, so why am I holding this position, right? Well, let's see why data scaling has worked in other domains. So this is a plot from the Llama 3 paper, where it's a classic scaling laws plot, where you see that when you increase the number of training tokens, you get a sort of reduction in the test loss or the validation loss, sort of like log linear sort of loss curves. And folks use this as the argument, oh, if you have any problem, if I just scale up the amount of data, it's going to work. But you have to see that this range of data over here is in the order of trillions of tokens, right? So this scale of data is just immense. The reason we have the scale of data in language is because everyone uploads text on the internet. But who among us has a robot at home uploading data to the internet? Not many of us, right? And so if you look at the regime of data in robotics right now, it's sort of like in this space where it's very far away from here. Okay? So because this is far away from here, there's a good and a bad, right? So the bad is, of course, we cannot just use a pure scaling argument. But the good is that there is now space for ideas. There's a space of ideas where if you have the right type of idea, there may be ways in which you can bootstrap out of existing learned models, bootstrap out of existing knowledge, and sort of bridge the capabilities of these robot models. Okay, so that's what I'm going to talk about today. Some ideas in trying to bridge this gap and trying to get high performance from robot models. Okay, so what's the principle over here? So the principle is, let's see how animals, creatures learn. My favorite example is this video of a cat trying to figure out how to open this door. And you'll see that it starts off with doing something reasonable. It tries to apply pressure on the handle, tries to do something reasonable. There's a human in the loop somewhere giving it some level of guidance, helping it along. And then eventually the cat figures it out. Then, of course, gets some reward from a fish bump. And then after that, it can now escape your home anytime it wants. Okay, so what's happening here? Clearly, this cat is not learning from scratch. It's not learning from trillions of tokens. It clearly has very strong understanding of the world already. So this type of learning is what we like to call a constructivist form of learning, and it's sort of built on three key ideas. The first idea: build as much as you can on prior knowledge. We already have these amazing VLMs, LLMs, GPT, all of this stuff. Let's build as much as we can on top of this. The second: if these LLMs do not know how to do something, well, you need to have very swift and easy ways to create and construct new knowledge and create and construct new data to supply this knowledge, right? And then third, you don't always need to have humans in the loop. One of the beautiful parts about robots and agents in general is that they can actually get their own data. They can actually interact with the world, get more information, and learn from that interaction, right? So are there ways to sort of also bootstrap on that? Okay, so I don't have too much time today, so I'll focus on the first two things. And for the rest, you can also see my website and find more information over there. But yeah, if you have questions, again, feel free to interrupt and ask questions. Okay, so let's get started with the first thing. So before I talk about how to use this prior knowledge, let me just show you a fun video which we ran early last year. So here is a robot. It's called the Stretch robot. It's a very janky, low-cost robot that you can fairly easily buy. It's very light, which means that you can easily carry it up a few flight of stairs, take it to your home. And just right out of the box, you can give it a text query like this: "Okay, robot, move the Takis on the desk to the nightstand." And what this robot will do is it will go around, it'll look around, try to find the Takis. So those who don't know, Takis is like Pringles, but so it's also like in a cylindrical can and has very Pringles-like looking chips in it. The reason we chose the word Takis is because this is something that LLMs are really good at. They can sort of associate words with visual really easily, and that's what we do over here. Okay, so you'll see this robot just robustly go and do this, and it can do it for like pretty much any text query that you give as input and try to provide. So it's all using what we call VLMs or vision language model. So if you see this image that I showed you earlier, right? You can easily feed these images into VLMs, and it'll tell you where objects are and what these objects are, right? So what we can do fairly easily is we can take this information and embed it into the 3D world around you. So instead of thinking of things as flat images, imagine you're looking at an image and you see, okay, that's like a chair, maybe that's a table, maybe. And now imagine I move around, right? So now as you're moving around, you assign the sort of language tokens of what that object was to the physical space of where you saw that token, right? So that you can imagine like a clip embedding of sorts in a physical space of where this chair is. Okay, so this is it's called a voxel map. So for every voxel in space, there's now a clip embedding inside it. Okay, now what this gives you is that if you have to query a new object, let's say you want to query the object plant. Okay, you just feed in the word plant, find the clip embedding of the plant, and then match that clip embedding in your voxel space. It will tell you that the plant is here. There's a small plant over here, and it's able to recognize that. And similarly, you could give it like other objects like umbrella. There's some umbrella over here. There's an orange laundry bag over there, and so on. Okay, so this is how we are doing it. There are other ways to do it as well. Like you can feed in the whole map into like a 4O-like model and ask it these questions. There are different ways of architecting this. It's a big emerging new area now, and if you're interested in research on this topic, there's a lot of things to explore. So then there's a question, okay, how do you actually pick objects up? Again, there are already learned models for this. We have worked on this in the past, but you can very easily just feed in like point clouds of the scene, and there are models already which will tell you how to grab it. And of course, you have to grab the right object. In this case, the Takis object. Well, you can just do a sort of intersection of the grasps and the object of Takis, and you'll find this really nice grasp of grabbing the Takis, and then you can sort of continue this process. So here, I'm just going to show you a snapshot of the robot just doing a bunch of things. So over here, it's trying to find a cooking oil bottle and then going to place it on a marble surface. Yeah, and after this, you'll see a bunch more other videos as well. Now over here, I'm mostly showing you only successes, but this robot fails as well quite a bit. And so when we started all of this work, the goal of this work was to understand what the limitations are. We're still a very academic lab, and so we really care about understanding where these models break. And there's a lot of like insightful ways in which these models break. So first of all, to get this insights, you have to run many experiments. We took this robot to many homes all around New York City and ran like a bunch of experiments on this. And we have this nice Sankey diagram of all the ways in which this robot can fail. Okay, so it can fail for several reasons. There's just a whole gamut of ways, from hardware failures to something going wrong in the navigation to when it's trying to place an object, it like tips it over as the hand moves away, right? So there's just many ways in which it can fail. But let me show you like my favorite way in which these models fail, which is this over here. So the way you query a language model has a huge impact in its recognition capability. Okay, so let's say you want to pick up this object over here. Okay, so this soda can over here, and you may think, okay, let me call it orange soda can, right? But that doesn't work as well. But if you call it metallic golden average can, it suddenly starts to work well. Okay, there was another really weird one, which was this one over here, where the main student who was working on it was like, I keep querying it, gray eyeglass box, but it doesn't find it. And then sometimes when I do it, it works. Sometimes it does not work. Do you see the difference? There's just like a space between eyeglass and eyeglass, and like this, apparently had a big impact on the performance. So again, the caveat here: this is all around a year old. Now these models are getting a lot better, so these failure modes could have also gone down, right? I think the way we query an object is going to be different, right? If I ask you to describe this object over here versus I asked you how to describe this object, you will both give me different answers. It may not be exactly the same answer. I think this is a fundamental question when we are dealing with these VLMs, LLMs. How do you get them to sort of understand your way of talking to it? Okay, so now what I'm going to talk about is how do we create skills, right? So all this high-level reasoning of, navigate to a point, pick something up, drop it there. I think these VLMs, LLMs are pretty strong at that. Let's talk about how do we increase the set of things it can do. Okay, so this is a project which we call RUMS. The idea here is we only train this model once, and once you train the model, hopefully this model works zero shot in new environments that is not seen before. Okay, so I'll just go over what it means to be zero shot. So here is a bottle that the robot has never seen before, and the task is what we call like fixing the object. So imagine like someone has like hit the object has fallen down, and you want to fix the object. And to sort of just show what I mean by a generalization over here, we're going to throw a beach ball at this object. So we know that it's actually randomized. So it's a random start position. This object has not been seen by the robot before, and the robot is now going to go and fix the object. Okay, yeah. And then you can keep repeating this experiment over and over again, and the robot just like faithfully goes and keeps fixing it. And now we also want to be robust to like other objects, other environments, and so that's what you're seeing here. You can use like other sort of can-like objects, and it works. And this recipe is fairly general. So this was for like reorienting, but here we have a model which can open any door which looks sort of like that, right? Anything with a handle, it can figure out how to grab the handle and open it. It can figure out how to open drawers and so on. So now you could like stitch these things together, and you could actually do quite a bit of stuff with it. And this is exactly what we are actively doing in our lab right now. So yeah, maybe like a few months from now, if I'm invited again, I can show you a cleaning demo. Okay, so now how do we do this? Okay, so we want to start from first principles over here. Let's say we do not know anything. Let's see how we can solve this problem. So first we have to get data. So how we get data is we have this tool. We call this a stick. So it's like a stick tool. It has an iPhone attached on it. So this is an iPhone in your pocket. We have an app which runs on the iPhone. What this app is actually collecting is the movement of the stick as you move around, and the visuals it sees. So all the RGBD information on your phone. And then let's say you want to solve a task. Well, we collect around 1,000 examples of solving this task. The key is to have lots of diverse environments. So in this case, we have around 40 environments that we take the stick in and collect these examples. The next thing is we train the sort of very interesting vector quantized transformers on this data. So this is a sort of involved architecture, so I won't go into the details. But the way to think of it is a normal transformer outputs text as output, right? So it's like probabilistic in terms of text, right? What this transformer model does is it's probabilistic in terms of actions. So it's able to capture diverse modes of human behavior, right? That's the maybe few second summary on the decubed algorithm. So we train this, and now here comes the sort of very weird and interesting part. So when we did all of that, we already got a success rate of around 60 to 70%. And I was like showing it to people, and they were like, the time it like fails by making a very, very small mistake. So is there a way in which it could just retry, just like try again? Okay, so here's where we were like, okay, what if we just like feed these failure images into like GPT-4o and just ask it, has it succeeded or failed? And so that's what we did. We just like took examples of what the robot saw, fed it into a GPT-4o, and just asked it, is the door open? And GPT-4o could very easily say, oh, the door is open or the door is not open. And so when the door is not open, well, it just keeps retrying until the door is open, right? And what we saw is it doesn't need too many retries. Very quickly, it can actually use this and get upwards of a 90% rate of success on new doors it's never seen before, in new homes, new environments it's never seen before. Okay. All right. So this strategy also comes with, so in this paper, we have a lot of other insights as well. So for example, how much data we need, what type of training objective you need. It seems like the training objective does not matter too much. What really matters is the size of the data set. So having more data increases the performance. But what matters even more than the size of the data set is the diversity and the quality of data. Having lesser data, but having that data in very diverse environments with lots of different objects, lots of different scenes and scenarios, that actually gives you the highest boost in performance. Okay, so there's also lots of other analysis over here. I'm just going to skip. This is a fun one where you can actually switch out this thing to different robots. So here we did it on the Stretch, the sort of cheap home robot. You can just take out the end effector. You can put it on an industrial robot. It works well over there as well. And all of this is fully open source. So the way to collect the data, the tool, the trained models, all of that is open source.